So gates. Recall we had a universal set of classical gates. Classical gates. And can anyone tell me what a universal set of classical gates is? Not. Another one? And that's universal, actually. But actually, this is not. If you look at it closely, there's another gate that's implicit, which is fan out. You put in a 0, you get out 2 zeros. You put in a 1, you get out 2 1s. Okay. Now, quantum circuits, well, maybe the equivalent of fan out in quantum circuits is cloning, so you can't use fan out in quantum circuits. So, not. So there is actually, so how do we do quantum circuits? Well, gates for quantum circuits. Well, the most important gate, maybe, is C naught, which is 1, 1, 1, 1. Zero, 0, 0, 1, 1, 0, 1, 1. So what does this do? Let's describe it. If bit 1 is 0, okay, let's say this is x and y. If x is 0, y goes to y. If x is 1, y goes to not y. Right? Because if x is 0, we're in this upper corner, upper left corner, and it's the identity. If x is 1, x being the first bit here, we're in this lower right corner, and this is a not. And this is a classical reversible gate as well as a quantum gate because, well, basically because it's a permutation, which means it's a classical. You don't get any phases applied to any of the things, and we don't get any superposition, so it's a classical gate. Okay. And quantum C naught is drawn like that. Not. And in fact, if you have an arbitrary unitary, you can draw it like this. And a controlled U would be drawn like that. And this, what does this mean? It means apply I to qubit 2 if qubit 1 is 0. Is 0. And if qubit 1 is 1, apply U to qubit 2. And if U equals alpha, beta, gamma, delta, controlled U is equal to, well, again, if qubit 1 is 0, that's this upper left corner. And if qubit 1 is 1, that's this lower right corner. And you can easily see that if this is unitary, then this is unitary. Okay. So the next thing I want to do is give some identities on gates. But first, maybe I should say something about the controlled NOT gate. So I'm going to say C0 can copy, well, not qubits, but classical information. So how does that work? Well, so I want to say 1, 0, C0 applied to 0, 0 is equal to 0, 0. C0 applied to 1, 0 is equal to 1, 1. Because this is a 1, you take the nut of this, you get 1. So C0 of x0, where x is equal to 0 or 1, is equal to x, x. So we can copy classical information. And if we want to copy classical information in a quantum circuit, we apply a C0. And we cannot copy quantum information, so that's as good as we can do. Question?
In the upper left instead of the identity?
You could, but then they wouldn't be control gates. They'd be called something else. So, I mean, alpha, beta, gamma, delta, alpha prime, beta prime. Why don't I? U prime, 0, 0. What this does is it applies U if bit 1 is 0, and applies U prime if bit 1 is 1. But this is really not called a control gate, a controlled U gate, although it's very similar.